Once you have precision and recall, you're stuck holding a pair of numbers. Compare two models, and one might win on precision while the other wins on recall, and now you're squinting, trying to decide which matters more. Wouldn't it be nice to have one honest number that captures both at once, so ranking your models becomes trivial? That's exactly what the F1 score gives you. But here's the interesting part. It is not just average precision and recall together, and the reason why is genuinely clever and worth understanding. Let's dig in. First, let's see the problem F1 is actually solving. Juggling a pair of numbers makes comparison hard. Model A has slightly better precision. Model B has slightly better recall, and you're left making a judgment call every single time. Across a dozen experiments, that quickly becomes exhausting, and it's easy to fool yourself about which model is really winning, because there's no obvious way to rank them. The F1 score fuses precision and recall into one number between 0 and 1. Higher is better, and now ranking your models is trivial. Just sort by the score. But the real magic is in how it combines them, because a naive average would happily let a lopsided model hide its glaring weakness, and F1 flatly refuses to allow that. It insists both sides pull their weight. So how is this single score actually built? Follow the construction one piece at a time. Start with precision. Of everything the model flagged as positive, how much of it was actually right? That's your first ingredient, and on its own it tells you nothing about the cases the model quietly missed. Then bring in recall. Of all the real positive cases out there, how many did the model actually catch? Now you have both halves of the story, correctness of the flags and coverage of the truth, and F1 is going to combine them into a single verdict. The question is how. Here's the twist. Instead of a plain average, F1 uses the harmonic mean. The harmonic mean punishes imbalance. It gets dragged down hard toward whichever of the two numbers is smaller, so a model can't coast on one strong metric while the other collapses. The result is one score that stays high only when both precision and recall are high. Take a model with 90% precision but only 10% recall. A plain average says 50%, which looks perfectly fine. F1 says about 18%, correctly flagging that this model is actually bad because it misses almost every real positive out there. That's the honesty you're paying for. Strip it down, and three ideas define the F1 score. It's the harmonic mean of precision and recall, not a plain average, but a combination deliberately chosen to punish imbalance and pull toward the weaker of the two numbers. It stays high only when both are high. A lopsided model, brilliant on one metric but quietly failing on the other, gets a low F1, which is exactly the honest verdict you want. There's nowhere for a weak side to hide. It's the honest metric under class imbalance. When positives are rare, plain accuracy is useless. You can predict all negative and score 99%, but F1 stays truthful by focusing entirely on the positive class through precision and recall. That's why it's the standard for information retrieval, medical detection, and language tasks. All right, let's lock in the essentials. The F1 score fuses precision and recall into one number, so you can compare classifiers without juggling two metrics at once. It uses the harmonic mean, not a plain average, which punishes imbalance and stays high only when both precision and recall are strong. That makes it the honest choice under class imbalance, where accuracy lies. It shines in information retrieval, medical detection, and language tasks. Its limits. It weights precision and recall equally, use F-beta to tilt one way, and it ignores true negatives entirely. If you enjoy machine learning explained this plainly, come explore more with us over at standarity.com. See you inside.